Welcome to In 5 Minutes. The agenda of this clip is to implement Cout for a full adder at the transistor level. Before we get started, I want to clear a basic which we have already studied. Suppose that this is my expression y, which is given as a dot b, and we want to implement this in the static CMOS style. We have seen in the previous clips what we do is we do a dot b, we put double bar on it. The upper bar will give me the inversion. We already know that, and the lower bar we simplify using De Morgan's. So what we do is this will stay as it is, the upper bar. This is a bar plus b bar. Now we hide the upper bar. Whatever is below the bar is nothing but my pull down. So a bar plus means parallel to b bar. And the upper one, the pull up would be exactly opposite to pull down. So down it's in parallel, so up it would be series. Again the inputs a bar and b bar, and this is my output. Output is y. My question is, what will happen if I don't invert my inputs and implement this straight away as my pull down? Let's quickly see that. So if y is equal to a and b, I am implementing a and b in pull down, and opposite to that in pull up. This is my VDD and this is my output. We know this expression is nothing but an AND gate expression where we clearly know that if this is my input A, this is my input B, and this is my output Y, 0, 0, 0, 1, 1, 0, 1, 1. If we quickly write it, only it would be 1 for this, all others would be 0. Let's take any one case. So input A is 1 and B is 0. Input A is 1 and B is 0. The transistor is off. This B transistor. This is on. A is 1 and B is 0, so this is on, and my output will be equal to VDD or 1. But I wanted my output to be equal to 0. I got an output equal to 1. Okay, let's take another case also. Suppose my inputs are 1 and 1. So 1, 1. Both are on. So this is on, and the output will be pulled to ground. So Vout will be equal to 0. So output is 0. However, we want the output to be equal to 1. So what we understand is, without the bar, if we implement, what we get is not V out or Y, what we get is Y bar. And in order to get Y from here, we need to connect another inverter which will give me a Y. So this is how it should be in order to get the same functionality without doing De Morgan's, etc. Let's see whether this was giving us the correct output for the same cases. Let's quickly see. Input A 1, B 0. A is 1, so A bar would be 0. B is 0, so B bar is 1. So let's put that here also, 0 and 1. Correct? So this is on, and this will pull my output to 0, so it was giving me the correct output. Same is the case when I take both my inputs as 1, 1. A is 1 and B is 1, that means A bar is 0 and B bar is 0. 0, 0, that means both of this are on, and my output is equal to VDD, so output is 1. So inversion and De Morgan's, that is double inversion, when we do, we get the same functionality. However, if we choose not to do De Morgan's, or not to put double bar and just express our expression straight away in pull down and its opposite in pull up, we get an inverted output to which we have to connect an inverter to get the correct output. This is the basic which we'll remember for the implementation of Cout and sum for a full adder. Remember that.